Complex eigenvalues. Up to this point, we've only discussed real eigenvalues and real valued vectors, including eigenvectors. But the linear algebra world we've established works over complex numbers of the form z equals a plus bi, where I squared is equal to -1. So example 3. Find the eigenvalues and a basis for each eigenspace in Cn of the matrix 5, -2, 1, 3. Then write the eigenvectors x in the form real part of x plus I times the imaginary part of x. Just as a notational note, the Cn here, the C, refers to complex numbers contrasted with Rn, which would be real numbers. So first, we need to find the eigenvalues. To do this, we need to solve for where 0 is the determinant of a minus lambda I. So we have 5 minus lambda minus 2, 1, 3 minus lambda. This is equal to 5 minus lambda times 3 minus lambda plus 2, which multiplies out to lambda squared minus 8 lambda plus 17. We can solve this quadratic equation using the quadratic formula. And so we would get that lambda would be equal to 8 plus or minus the square root of b squared, 64, minus 4 times a times c, all over 2 times a, which simplifies to 4 plus or minus I. So we have complex eigenvalues. So we've got those complex eigenvalues, part 2. Now we need to find the eigenvectors. So to find the eigenvectors, we need to find the null space of A minus 4 plus or minus. We'll start with the plus, 4 plus I times I, which would be 1 minus I minus 2, 1 minus 1 minus 1 minus I, like that. Okay. We can swap our rows because we need to row reduce this. We can swap our rows. So we can do row 1 swaps with row 2. And so this would be the same thing as 1 minus 1 minus I, 1 minus I, and minus 2. And we can play an interesting little game here. We can let me show you the shortcut. We know that the eigenvalue is going to create a determinant of 0, which means there's going to be only one pivot. And we can see the one pivot that we have here, so that we know, unless we made a mistake, which in this case we haven't, we know that the second row must be a linear combination of the first row. So believe it or not, seems kind of wild and crazy, but believe it or not, we just can know that the second row, after some basic row operations, will be 0, 0. Again, because there's only going to be one pivot because of the way this matrix was constructed. Well, that was kind of convenient. So now notice that we could make a linear combination that added to 0 if we took 1 plus I of the first column and 1 of the second column, that would add to 0. So our first eigenvector, is 1 plus I and 1. Okay. We could go through the work to find our second eigenvector, but note these things come in complex conjugate pairs. So the other will be 1 minus I and 1. Notice here's a plus and here's a minus. Further notice that the well, I was going to say further notice that the plus goes with the plus. I don't know that that will always be the case, so I don't want to get you too excited about that particular thing. So this tells us that our eigenvectors are x equal to 1 plus or minus I 1, which we could write as 1, 1 plus or minus I times 1, 0. In this case, notice that the plus did indeed match with the plus eigenvalue. We might need that information down the road to know which one was matched with which. This first part is called the real part of x. And the 1, 0 is called the imaginary part of x. Please note here that that does not include the I. The I is not included in the imaginary part of I. The I is just, or the imaginary part of x is just real numbers. So let me back up to make sure that you see what we did. We started with a matrix up here, and we first found the eigenvalues, which were complex. Then we found one of the corresponding eigenvectors. We used a relationship of what we know about how eigenvectors are formed or how eigenvalues are formed to do our row reduction kind of intuitively. We also found the second eigenvector by knowing they came in complex conjugate pairs. I didn't prove this, it's just true. And so we have eigenvectors at the end of this day, sorry, eigenvalues that look like 4 plus or minus I, and we have eigenvectors that look like 1, 1 plus or minus I, 1, 0. That's the end of this particular example. Notice that a real valued matrix can have complex eigenvalues, 4 plus or minus I, and eigenvectors, 1, 1 plus or minus I times 1, 0. The matrix was all real numbered, but the eigenvalues and the eigenvectors were complex. Notice further that the eigenvalues and the eigenvectors came in conjugate pairs. Conjugate pairs, things like A plus or minus B. In this case, it's complex conjugate, so it's BI. At the end of this lesson, we're going to put a whole bunch of things together and see this kind of cool relationship where some matrices can be factored and involve a rotation scaling matrix. In order to get there, we need to unpack this idea of a rotation scaling matrix. So let's begin by finding the eigenvalues of C, where C is the matrix A minus B, B, and A. So to do that, we'll follow the same process, where first we'll find our eigenvalues. And so we need to solve 0 equals the determinant of A minus lambda minus B, B A minus lambda. This will be equal to A minus lambda squared plus B squared. And you could actually solve this for lambda by noticing that we've already got a completed square, I guess. So you'd notice that that A minus lambda quantity squared is equal to negative B squared, which would tell you that A minus lambda is equal to plus or minus the square root of negative b squared. So this tells you that a minus lambda is equal to plus or minus I times the absolute value of b. Remember, the square root of a square is the absolute value of the quantity. And then we could solve that for lambda. So we would get that lambda is equal to a, now it's minus plus I absolute value of b. But if we assume that that b is positive, well, it's not like if b is negative, then this is going to posify it. Oh, sorry. If b is negative, so sort of two options. Sorry, my tablet's being cranky. If b happens to be positive, then you'll still get a minus or plus b, which is the same as plus or minus. If b happened to be negative, then this would be the same as changing the sign or plus or minus ib. So if we assume, so we're going to get either version, but we can assume that if b is positive, we would just have lambda equals a plus or minus I times b. If b was negative, it would work out to be the same thing. But we're just going to assume it's positive for the sake of where we're going. So we started with this matrix A minus B, BA, which I'm claiming is a rotation scaling matrix. And so far what we've discovered is that lambda, the eigenvalues, are A plus or minus IB. So next up, I want to try to understand where theta fits, or an angle fits into all this. So let's call R the absolute value of lambda, and the absolute value of lambda, or the modulus of lambda, would be the square root of a squared plus b squared. And then we're going to use the picture below to find a over r and b over r in terms of the angle phi. So remember that we can label our axes with the real part and the imaginary part instead of x and y. And so we have our real part. Maybe I'll change my colors. We can have our real part is the A, so that's here. And we can have the imaginary part, that's the B. So that would be there or here. There's my B. So that's why the picture is the way it is. And so then you can notice that A divided by R would be the adjacent divided by the hypotenuse. So this would be the cosine of phi. And B divided by R would be the opposite divided by the hypotenuse, or the sine of phi. Notice that these formulas assume a positive b because of the magnitude of b in the derivation. So again, we assumed that b is greater than 0 since we had a absolute value or magnitude of b in the derivation. So now we can look back at the C matrix, A minus B, BA, and we could factor an R out of each of those terms. So we could factor an R out, and we would be left with C equal to R times A over R minus B over R, B over R, A over R. So we just pulled out that factor of R. And so we could write this as R 0, 0, R times A over R minus B over R, B over R, A over R, but that would be the same as cosine of phi minus sine of phi, cosine of phi. Okay. Where, good news, you probably recognize this, that R0, 0, R is a scaling matrix, and the cosine phi minus sine phi, I'm going to cram this in here a little bit. Sorry about that. Cosine phi is the rotation scaling matrix, or is the rotation matrix. Example 5. The matrix -5, -5, 5, -5 is a rotation scaling matrix. Find its eigenvalues, scaling factor, and the angle of rotation phi. So we want to start by pattern matching. So remember, the general form of our rotation scaling matrices is A minus B, B, A. And so we're saying, well, this would be equal to -5, -5, 5, -5. And we could, like, if this is going to be the case, that tells us that our A is -5 and our B is 5. Furthermore, we're going to get that our R, our scaling factor, would be the square root of A squared plus B squared, or -5 squared plus 5 squared, square root of 50, or 5 root 2. So that'll be our scaling factor. And our matrix could now be written as 5 root 2 times -1 over root 2, -1 over root 2, 1 over root 2, -1 over root 2. So this is telling us that our cosine of phi is equal to -1 over root 2. So if you think about the unit circle, cosine gives you your x coordinates. So here's your minus, let me draw that picture again. So if you think about your little unit circle, cosine gives you your x coordinate. So here's your -1 over root 2. And so our 2 points would be here and here. These are our possible phis after just looking at cosine. And then we know that the sine of phi is equal to +1 over root 2. So again, thinking about the unit circle, sine gives you your y values. So here's your 1 over root 2. And so the possibilities are here and here. And the only possibility between those two that's in common, so you have all these values, the only one that's in common is, of course, right there. So that tells us that we can combine these two thoughts, and we can get that our phi must be equal to 3 pi over 4. Okay. So we have the scaling factor of 5 root 2, and we have the rotation, the counterclockwise rotation of 3 pi over 4. This brings us back to the idea of matrix factorization. Recall that if A had real eigenvalues and enough linearly independent eigenvectors, then A equals P D P inverse, where the columns of P were the eigenvectors and D was a diagonal matrix whose diagonal entries were the corresponding eigenvalues. Similarly, let A be a real 2 by 2 matrix with complex eigenvalue lambda equals A minus B, B not 0, and an associated eigenvector V in C2, then A equals P C P inverse, where P is equal to the real part of V times the imaginary part of V, not times, pardon me. First column of P is the real part of V. Second part of column of P is the imaginary part of V. And C is the rotation scaling matrix, A minus B, B, A. One thing to note here is this minus sign in which eigenvalue we're actually going to choose. Notice we could derive this formula, but at the moment, I'm just asking you to take this formula and use it. You could derive it on your own time. I'd be happy to derive it with you outside of class or in person. But we're just working with it here for the sake of seeing the beauty and not getting hung up in some of the details. Example 6. Find an invertible matrix P and a matrix C of the form A minus B, BA, such that the matrix 5, negative 2, 1, 3 has the form A equals P, C, P inverse. So notice this is a matrix that we've played with before. And so we already saw earlier that this has eigenvalues that are 4 plus or minus I. Okay. So the eigenvalue that we care about is the 4, the minus version, the 4 minus version. So 4 minus I is of the form of A minus BI. Remember, we assumed that our B's were positive with A equal to 4 and B equal to 1. And it has corresponding eigenvector. Eigenvec is, we have 1, 1. Remember, we had plus or minus I times 1, 0. And what we want is we want the minus sign here because we want the one that we want to be tied with the negative eigenvalue. And so we could rewrite this as 1, 1 plus I times, we bring the negative inside, negative 1, 0. So here's this whole thing is our eigenvector V. And so the 1, 1 would be the real part of V. And the negative 1, 0 would be the imaginary part of V. So thus, we're saying that A is equal to P, C, P inverse, where P is equal to 1 minus 1, 1, 0. And C is equal to 4 minus 1, 1, 4. So I just want to back this up and make sure that you're seeing what happened. Once again, we took our lambdas to be the one with the negative eigenvalue. And so that's why we were always using the minus signs all the way throughout. And then when we built our P matrix was built with the real part of V. So that's the 1, 0. Or sorry, the 1, 1, my bad, 1, 1. And then we had the imaginary part of V in column 2. That's the minus 1, 0. Imaginary part of V, minus 1, 0. And our A matrix was of the form A minus B, B, A. And so here you have A minus B, B, A. So if you can take the matrix and you can find the eigenvalues, you can find the eigenvectors, it should be really easy to figure out what your P and what your C matrix are.